So this is 7.3.2 electric field strength. It is just like gravitational field strength. So, gravitational field strength, let's remind ourselves what the definition of that is. Force acting per unit mass in that field, or at that point in the field. So in the same way, the electric field strength is the force acting per unit charge, or per unit positive charge in this case, because for gravitational fields there was no positive and negative, but in the case of electric fields there is positive and negatives because this is a vector, so we have to say per unit positive charge placed in that field. Sometimes this is referred to as a test charge. So a charge that's small enough and positive that we know how it will behave in the field, but it also won't affect or change the field that it's placed into. So the equation here is that the electric field strength, which we denote as E, is equal to F over Q. This is similar to G equals to F over M in a uniform field. And in a non-uniform field, so in a radial field, it's E equals to Q over 4 pi epsilon naught R squared, which is basically the same as G equals to GM over R squared.
So you know how there's epsilon naught? Is there like epsilon 1, 2, 3?
No.
So why isn't it called epsilon?
Because it's called epsilon naught. Because epsilon can refer to the permittivity of other things. The relative permittivity.
Is that epsilon also EMF, no? Yeah, it's also EMF.
And that. But we're not talking about EMF here. We're talking about a constant. Now, the electric field strength has 2 units. So E is measured in newtons per coulomb or volts per meter.
So you could convert to each other without being confused.
And just like before, there are 2 types of fields that we're interested in, which are radial fields and uniform fields. Two types of fields, which are uniform fields and radial fields. The radial fields has 2 subcategories, which is the radial field of a negative point charge and a positive point charge.
same, just one is positive and negative.
Exactly. So they do, the radial fields will look very similar. So for the uniform field, we need two parallel charged plates. One plate is positively charged, one is negatively charged. Now this can be rotated where the positive can be underneath and the negative can be above, or it could be sideways, it doesn't matter. As long as it's two plates that have opposite charges. Or sometimes you would even see where one plate is relatively more positive than the other one, or relatively more negative than the other one. So for example, what I've labeled as a positive plate could be 100 volts. What I've labeled as a negative plate doesn't need to have a negative charge. It could even be 0 volts. But that will act as a ground and it will behave as if it were a negative plate. So in this situation,
So could you have
the field lines go from the positive plate to the negative plate, like so. And because it's a uniform field, I draw them equidistant. And the lines point towards the negative plate. Reason for that is the electric field lines describe the behavior of a positive test charge. So if I were to place a positive test charge anywhere in that field, the force it experiences will be towards the negative plate. So even though the lines and the arrows show you about a positive charge, you would then know that if we were to put a negative charge in there, it would do the opposite of what the arrows show you.
So you have like for a positive it would be like 100 and negative would be like 50.
Yeah. Then for a negative radial field, we have our negative charge. And this very much looks the same as the gravitational fields that we did before. And the arrows all point towards the center of that charge. Because if we were to place a positive test charge anywhere in that field, it will move towards that negative charge. And very similar to that, we'll have the positive radial. So in this case, I'll draw a positive charge. And again, we have a radial field. However, in this situation, if we were to place a positive test charge in that field, it will experience a force moving it away from that positive charge creating the field. So the arrows will be pointing away in this case. Right, we can start a new page. And we'll do the analogy between E and G fields. And we'll start with similarities between them. So we'll do gravitational fields on this side of the page. And we'll do electric fields on the right side. So first we look at the equations and how the equations are similar. So you've got F equals to G M1 over M2 all over R squared. And for the electric fields, we've got F equals to Q1 Q2 over 4 pi epsilon naught R squared. So the relationships are the same here. So in the case of the gravitational force, the force is proportional to the product of a gravitational charge. Gravitational charge is just mass. In the case of the electric fields, the force is directly proportional to the product of the electric charge, which is what we typically just call charge. And in both of them, it's inversely proportional to the square of separation. So while this might seem like a difference, what I'm about to write, it's actually a similarity because they both affect their respective charges. Yeah? So the charge for a gravitational field is the mass, and the charge for the electric field is the electric charge. Then the behavior of the gravitational field strength and the electric field strength are the same as well. So G is equal to F over M in this case, and E equals to F over Q in that case. Their units are also very similar. So in this case, G is the force per unit mass. Which is newtons per kilogram. And here it's the force per unit charge. Which is newtons per coulomb. So the force on this side could be given as M2G equals to G M1 M2 all over R squared. And the force on this side could be given as E Q2 equals to Q1 Q2 over 4 pi epsilon naught R squared. Then for the potential, it's minus Gm over R in this case. For the electric field, V is equal to Q over 4 pi epsilon naught R. Now in the case of the electric field, we don't have the negative symbol for the potential. And the reason for that is because the electric field can be positive or negative, the electric charges. So depending on what we're talking about, it could be a case where you need to do work to bring it to that field, or work is done by the charge creating the field. So if we think about the two radial fields, let's think about the negative field. The negative field behaves just like the gravitational field, where our positive test charge does not need to do work to come to that field. The charge that's creating the field in the first place will do the work. But in the case of having a positive charge creating a radial field, then to bring a positive test charge to that field, then we need to do work, or the test charge needs to do the work to come there.
So is the potential in the gravitational one
It's the same. But in the gravitational, you never need to do work to come to the field. The mass that's creating the field will do the work for you. So the negative will only appear in the electric field one when you have a negative charge creating the field. Then you have a negative potential, which means work's done for you. But then if you start talking about a negative charge coming to a negative field, then a negative charge has to do the work. Right? So it matters about the symbols this time. Hence why there is, by default, there is not a negative there. The negative will appear and disappear depending on the combination of the charges that you're putting in there. In both of these cases, a point mass makes a radial field. And for the electric field, a point charge creates a radial field. However, I'm not going to put arrows for the point charge because the arrows will depend on whether that charge is positive or negative. So I'm going to leave it like that. Now let's talk about the work done in these fields. So work done in a gravitational field is the gravitational charge, which is the mass that we're trying to bring to that field or bring away from that field, is m delta v. And for the electric field, the work done is going to be q delta v. And then we have units for these as well. So this is kilograms multiplied by a joule per kilogram, which gives us a joule. In the case of the electric field, we have a coulomb. Now thinking back to electricity, what's the definition of a volt? Back to AS physics. Work done per unit charge. Joule per coulomb. Oh, I made a mistake here. I put Q instead of C. Coulomb is a C. There we go. And we glitched. All right, so that's a C, coulomb, and here is a joule per coulomb, which equals to joules. And then we can end that bit over there. Now we'll look at the differences. So we'll do gravitational fields again. And electric fields. So gravitational fields can be attractive only. The electric fields can attract or repel. Gravitational fields cannot be shielded. So that basically just means there is no way for you to put something in front of you to prevent yourself from experiencing a gravitational force when you're in or near a mass that's creating a field. But you can with electric fields. And this can be demonstrated very easily at home. Take two mobile phones, take some aluminium foil, wrap one phone in aluminium foil and try to give it a phone call, and it will not connect. So this can be shielded, which can be done with metal foil or a Faraday cage.
If you know when you drive you in your car and you like the radial or something, you're driving on like a bridge. Is that the electric field being?
Say again?
Do you know when you're in the car and you're driving under like a concrete bridge and you have like the radial on and it's blocked? Is that the electric field being shielded?
It can be. It doesn't necessarily have to be.
Okay.
Now, most of the time, if you're talking about concrete bridges, it's not that the electric field is being completely blocked. More of a case of it being attenuated because it has to penetrate through the concrete. Now, if the electric field is strong enough, it will pass through the concrete and you won't have it blocked. But when I'm talking about shielding, a thin piece of foil will completely get rid of that electric field from passing through it. It will absorb it. And so you won't have any signal on a mobile phone if you wrap it in foil.
Okay.
Now notice that a lot of electronic devices these days are made of metal. So mobile phones, for example. But mobile phones still need to receive a signal. So when you look on the sides of a mobile phone, while the sides are made of metal, you'll see like there'll be a little strip that's not metal on the side of your mobile phones. And that's where they place the antenna. Or when they're creating the mobile phone, they actually use the casing of it as an antenna. Because you can't put an antenna inside it because the metal casing will act as a shield and shield it. So if there's let's think of another application of that. Desktop computers are basically a metal box. You never have internal Wi-Fi on desktop computers. The antenna is always located on the outside. Even if you have Wi-Fi built in, the antenna will always be external. You can't have an internal antenna in a motherboard sitting inside a metal case. It will be shielded and it won't pick up any signals. And actually, cases are designed to behave like a shield anyway. Because you have so many high power and high frequency devices running in a computer like processors, graphics cards, etc., they create electromagnetic interference. And you don't want that interference to leak outside of that case because it will affect other things. For example, it could affect broadband quality because it could interfere with broadband signals in wires. It could even affect TV signals. So there are cases where if you open up a computer and you place it near enough to a TV, sometimes that electromagnetic interference will affect your TV channels from being picked up properly. So it's designed like that on purpose. All right, we'll start a new page. And now we're going to look at uniform E fields. So we'll do an example here. We've got positive plate and the negative plate. And they have a separation between them of D. Here we put plus 1000 volts, and on the bottom we'll put negative 500 volts. So the electric field is worked out by the potential difference, so delta V, over the separation D. So So in this case, if we're looking at this particular example, you will do the potential difference, and the difference between the two plates is 1,500 volts, divided by the separation D, whatever that value would be. And charged particles moving between plates will have different trajectories depending on the charges of those particles. So the trajectory actually depends on multiple different things. It depends on the charges, but funnily enough, it also depends on the masses. And you're going to see why in a moment. So if I do our positive and negative plates, and we draw our field lines, let's start with a proton. So here's our proton. If we have a proton moving towards these negative plates, once it enters that uniform field, it's going to experience a force. And proton is positive, so the force it experiences is in the direction of the field lines. So it has a horizontal velocity, and then it starts to experience a vertical force acting down. If there is a force, a resultant force, it also experiences an acceleration. And the acceleration is experienced in the vertical downward direction. So it begins to accelerate downwards. And it accelerates downwards according to F equals to ma. And then it behaves just like a projectile. So F is equal to EQ, and also F equals to ma. So the acceleration it actually experiences depends on its mass. So a less massive object in a field like this will experience a larger acceleration. And we'll see that with another object. So if we had an electron going to the field. Now when it enters the field, the electron has a negative charge. And its negative charge has equal magnitude to the proton. So it experiences an equal magnitude of force like the proton, but upwards. However, that equal magnitude of force is then divided by a much, much smaller mass. So it experiences a greater acceleration. It still behaves like a projectile, but it starts falling upwards rather than falling downwards. And it falls upwards more rapidly than the proton does. So this projectile will curve much, much quicker than the proton.
What isn't the mass of it? It's smaller.
It is, and so it experiences a bigger acceleration with the same force. It's easier to accelerate less massive objects than it is to accelerate more massive objects. So the electron experiences a larger force because it has less mass. Sorry, a larger acceleration because it has less mass. The force is equal.
So can you equal the two forces?
They are equal.
Yeah.
Yes, they are. So F equals to EQ, but then that EQ also equals to MA.
Also, you can have
So EQ over M gives you the acceleration. Well, E is constant because that depends on the electric field between the plates. Q is the same for a proton and an electron. And then it's just the mass that's different. So the mass determines how much acceleration each of these will experience. Now if we put those equations together, and we'll do that now, F is equal to EQ, and E equals to delta V over D. If we put these two together, we get F equals to Q dV over D. Now look what happens when we start moving these things around. If I move the D and multiply it to F, we get force times by distance equals to Q delta V. Now the force is vertical, right? The separation is also vertical, right? So the distance and the force are parallel. Force times parallel distance is what? Work done. So the work done is equal to Q delta V. Oh, hold on. QV, when we're talking about potential difference, and here delta V is potential difference. We'll go back to electricity from year 1. Work done equals to QV. And in this case, Q delta V. So we got our electric equations out by doing this. So put a box around that one, and we'll put a box around this one. And that's the end of 7.3.2.